3D. You get another.
Okay, good afternoon, everybody. We are about to start the afternoon session with and I have pleasure to introduce you Andrea Bertozzi from UCLA and the Untitled talk. Please, Andrea.
Thank you. Can people hear me? I think the mic is on. In the back, it's okay? Okay, great. Thank you. So, so you see the title of my talk. So this is kind of a different topic for a PDE workshop, in that I'm going to be speaking about problems in machine learning, in particular things like large data classification, so high-dimensional data where you want to segment the data rather quickly and efficiently into a finite number of classes. So there are many applications. I'll start with some examples in semi-supervised machine learning, but I'll also go on to some examples from community detection and social networks. Also, exploiting the graphical structure. And the work that I'm going to speak about is motivated by a lot of sort of historical work in PDEs and free boundary problems, in diffuse interface methods, and in particular those kinds of ideas that have already been very successfully applied to problems in image processing, problems involving things like 2- and 3-dimensional images in Euclidean space. So, and the work that I'm speaking about today is pretty much all done in the last few years, in the last three years or so, with a number of colleagues now. So I have a list of a lot of people here, a bunch of students at UCLA and postdocs, and my Navy collaborator, Arjuna Flenner, who was really instrumental in getting me into this area, and also some faculty collaborators. The other thing I wanted to say is that there are very specific people at UCLA whose earlier work has really inspired a lot of this. Stan, I'm sure probably the most, but also Chris Anderson, who's some of his recent work we're using, and Luminita Vesse and Tony Chan, their earlier work on segmentation. So I'm going to start with just a little review from the image processing literature. This will make you a little more comfortable. Hopefully people who are not so familiar with image processing, you'll see where these ideas can be used in big data classification. So so the name of the game in many of these instances is variational, meaning that we want to solve some kind of data problem where we have data, but it's typically noisy or maybe incomplete. And we'd like to construct some function that is nice, that's nicer than the data, that maybe represents what we hope might be the ground truth that we don't know. So these are three of the most famous variational methods that I know of for image processing in 2 dimensions. And these in particular, the top one and the bottom one, this one in particular, very highly influential in the work we're doing now on data segmentation. So I wanted to just review these ideas. So in these examples, what we have in all cases is we have some given data, which is a 2-dimensional image. Again, this is the review part of the talk, and we'd like to segment it. So it's a very simple binary segmentation problem. The Mumford-Shaw functional, what it tries to do is it tries to find a curve like this one here that would separate the two parts of an image, and then it tries to find a smooth function f, a function that's smooth away from that curve. So you can see this energy functional has 3 parts to it. This is often found in all of these problems. It's a least squares fit to the known data, which is G. G is our known noisy, perhaps incomplete data. So simple L2 functional. This term here is demanding that f, the unknown, is smooth away from the edge, which is gamma. And finally, a very critical part of the model, which we see in many of these classical segmentation problems, is a term that demands that the length of the perimeter of this segmentation, the boundary, be relatively small. So this term measures the length of the perimeter. Okay? This is a Lagrangian method that's very famous, invented by Dimitri Tertsopoulos. He's also now at UCLA, although he was not when he did this work, earlier work. The Tertsopoulos snakes which have a big presence now in medical imaging, These are sort of a Lagrangian parameterization of a curve. This is the energy associated with the curve. It's not this length, so it's a different energy, but still it has, this is sort of a curvature kind of term in the energy. This is the tangent to the curve, the integral of the square of the tangent to the curve. And then this penalty term here, I didn't put in any details, but typically might involve this kind of a least squares fit to known data. That's Terzopoulos snakes. And again, the Chan-Vessey segmentation, this one was published in 2001, just to give you an idea of the time scale here of this work. This is basically a simplification of the Mumford-Shaw model, because what we're doing is we're approximating the entire problem like this over here. We're approximating our image in a very simple way. We're approximating it as piecewise constant, two unknown constants, C1 and C2, and a curve gamma separating those two unknown regions. And then you can see that the energy functional to minimize involves, the least squares term for these constants, which need to be determined. F in this particular example now is F is the known data, the noisy data, and then again the length of the boundary, the perimeter of the boundary between these regions. So you see this perimeter term, and the perimeter is very, very important, because if you think about noisy image data, right, if we put salt and pepper noise on top of a simple characteristic function like this, suddenly the boundary becomes very, very noisy and jagged, right? And so you have to introduce some kind of a regularization to make the problem well posed, and the natural thing to do is to enforce some kind of smallness on the length of the boundary. So as soon as we start looking at something like the length of the boundary, we start talking about functionals like the total variation functional, right? If I have a characteristic function like this one, and I want to measure the perimeter of the boundary of the regions between the 1 and the 0, one way I can do that is by computing the total variation functional of that characteristic function. So this is background. Another piece of background, which should be familiar to many of you, but perhaps not all of you, is the connection between, so here is total variation written out, okay, in terms of the integral, is the connection between total variation and the Ginzburg-Landau functional, the diffuse interface approximation to that. So I like this connection from a functional analytic point of view. What we're doing is we're replacing the L1 norm of the gradient here with an L2 norm, very, very different functional, which will, of course, enforce some smoothness that you don't have in this case. But then there's a small parameter epsilon, which determines the length scale over which you see the smoothness. But this has to be competing with another term here with a very large number in front of it, where W is typically a double well potential that would force you to want to live in one of these two values, say 1 and 0 in this case here, where 1 and -1 depends on the particular convention that you use. Okay, so this is also classical. This one can actually prove gamma convergence of this to this functional. This is a classical result from PDEs, and that result has been, of course, used in many examples in the physical sciences, but also in image processing as well. So I wanted to just review a few pieces of work from the last decade, and what we see in terms of the PDEs is when we have the Ginzburg-Landau functional rather than total variation, you compute the first variation of this, which is relevant if you're going to do a gradient descent method. And you get the all-in-Kahn equation, which is lovely because it has a heat equation, very easy to solve. And then this local term, which is basically the gradient of the double well potential. And another class of models that we use in physical sciences are the H-1 gradient flows of the Ginzburg-Landau functional, namely the Kahn-Hilliard equation and its variance. The Kahn-Hilliard equation also has shown up in image processing in the last 10 years. In fact, it's work in my group, and it works quite nicely for problems where you have more than one boundary condition across an unknown region, like an in-painting problem. Here are some examples with here's blind deconvolution of barcodes. This was published 10 years ago by Salim, who was at the time a postdoc with us. He's now on the faculty at Michigan. And the barcode problem is an ideal one for something like this binary model, the Ginzburg-Landau model, because the barcode is a binary signal that you're trying to recover. So in his model, he uses the Ginzburg-Landau functional for the binarization of the solution, and then that added to it a least squares fit to the known data, where this is just a blurring kernel. So K is the blurring kernel, and U is the solution you're trying to recover. So you minimize this functional, and hopefully you get something that looks like the clean barcode given a noisy and blurry signal F. And the other piece of sort of very famous result from PDEs that I want to use to study large data on graphs is the threshold dynamics idea, coming from a paper by Merriam and Benson-Osher from about 20 years ago. And their idea was that if we think about something like the Allen-Kahn equation, one of the things that we know from Allen-Kahn is that it approximates motion by mean curvature of the interface. This is also a classical result. But there's another way. So when you're trying to solve Allen-Kahn to do motion by mean curvature, you have to worry about the small epsilon here, the large epsilon here, and numerically resolving that in terms of this Laplacian term here. So there's another way to do motion by mean curvature without the small parameter epsilon, and that's basically the MBO scheme. And it's a very, very, very simple idea. And the idea comes from the fact that here we basically have dynamics that involve a competition between the heat equation and this double well, which is pushing everything into one of two local minima. Well, why not replace that ODE dynamics with something really, really simple, which is just thresholding? Why not just put everything into one of the two wells? So it turns out, almost magically, if you alternate between solving the heat equation and thresholding in the right way, you get a good approximation of motion by mean curvature. And so that goes back about 20 years due to Merriam and Benson-Osher, and that's been rigorously proved as well. And in fact, this idea was used for image processing and image segmentation, coupled with the Chan-Vesse model in a JCP paper by Esadoglu and Tsai in 2006. So this is all background. And I think I'm going to skip the in-painting because it's not quite as relevant for what I want to talk about. All right, so we have this beautiful literature from phase field, from PDEs, from curvature, driven motion applied to problems involving low-dimensional images in the plane. And so I argue, and my colleagues as well, that actually there's a beautiful parallel between all of that work and what we need to do now for high-dimensional data segmentation. And so my work in this area started with a paper that I wrote with Arjuna Flenner. He works for the Navy in the United States at China Lake, but he's a scientist. He's got a PhD. And we published this in MMS, and we were really, really excited to learn just a few weeks ago that we're getting this prize, so I'm going to do a little advertising for that. And I think the reason why is maybe not so much the paper itself, but the impact that it's had on the work that came after that. So I'm going to try to explain all of that now. So let's start with the big data problem and what we're trying to do and how we're going to set up the math problem. So what we have is we have a sort of a discrete collection of a lot of pieces of data, each of which has similar structure to the other ones. So here are some examples. So I like this one because we have a lot of data on the US Congress. The US Congress is big. The House of Representatives is 435 members, and they vote, right? So you can, and not only that, but we have ground truth. We know what party they're in, for example. We know what state they come from. And we can look at the vectors of votes as sort of high-dimensional data associated with everybody in the Congress. So that's not an image processing problem. There also is another class of image processing problems that you can map onto a high-dimensional graph, and those are the non-local means graphs for analyzing texture in images. And so the idea there is that every pixel in the image is a piece of data in the graph, And then what we do is we look at neighborhoods around each pixel. And this is an example that's very high dimensional when the pixels actually are not just grayscale or RGB color, but hyperspectral. Sometimes you have examples, and I'll show you one, where we have images where every pixel might have 128 bands in the EM spectrum, so very high dimensional pixels. And then you can look at patch neighborhoods around them, so that gives you a gigantic feature vector associated with every pixel, and then we can construct a graph associated with this data set. So now, how do we construct the graph? Well, a graph is literally just nodes with weights connecting the nodes. So the weights take on values between 0 and 1, and they should be related to the nodes. So a popular kind of graph that people study for large data is called the similarity graph, and here's an example of how we would construct the weights for a similarity graph. Basically, I have to have a metric that measures the difference between the data at node X and the data at node Y. So you have to give me the metric. And that's part of the problem in modeling these things, is coming up with the best choice of the metric. So you get the metric between any two pieces of data, and using the simple formula, I can compute a weight. So what this tells me is that if my two pieces of data at the two different nodes are identical, then I should have a weight of 1. Right? And if they're really, really far apart, then that weight should be close to 0. So that's the idea. It's measuring how similar. It's a similarity graph. That's what it is. Okay, so now what do we do with the similarity graph? Well, we try to find a minimal cut. Okay? And so these are pictures you can pull off of Wikipedia. I found them there, showing what a minimum cut might look like for this very simple toy model, or a maximum cut where you try to cut in a weird way. Basically, what you're doing is you're assigning, in the cut problem, you want to assign every node on the graph as being in one of two sets, and we're going to color them white and black in this example. And then we want to add up all of the weights that we have to cut when we pull apart those two different sets. So if you actually write down the formula for that, this is the formula that you get. So what we're doing is really coming up with an assignment function, f. You can think of this just like in the image processing problem, phase field or whatever, where you're going to assign some of those nodes as 1, some of the other nodes as 0. So f would take on binary values. And then the minimum, so then the cut, the measure of the cut is just the sum of all the weights times the difference between the f's at each of those nodes that connect that particular weight. And so the minimum cut is going to be the minimization of this functional here, and that is nothing other than the total variation on the graph. Okay, so now you see that what we're going to do. So in the image processing problem, the length of the perimeter was a very important thing in our variational model for image segmentation. In these machine learning problems, we're going to replace that with the minimal cut. Okay, we're going to try to minimize the cut as part of the solution of the data classification problem. Now, it turns out that some of these ideas have a prior presence in the literature, but maybe not quite from this perspective. So I will mention that and it's all through image processing. So for example, the non-local means functional, which is basically a special case of this similarity graph, but applied to examples in imaging. The non-local means functional was introduced in 2006 by Boades, Collin, Morel, but they did not look at the total variation applied to that. They looked at an H1 semi-norm applied to this. And then, not surprisingly, my colleague Stan Osher and one of his then postdocs, Gilboa, looked at this paper and said, hey, why aren't they doing non-local total variation? And so they introduced their own ideas about how to do that. And one of the problems that they actually had some lovely papers, so the results were really quite striking. You could take images with textures and you could remove patches of the texture and you could bring it back using the non-local means functional in a way that you just can't do with any kind of local, any kind of local approximations. So these were really nice results, but the code was slow. That was the problem. Even using some of the fancy compressed sensing algorithms that we have in the last 5 years, the code is still pretty slow. So one of the things I'm going to show you is that using some of the new stuff coming out of machine learning coupled to some of the machinery that I'm going to show you, we can speed up. One of the results we get is their algorithm we can now run about 5 times faster on things like grayscale images. All right, so now, so what did Arjuna and I do a few years ago? And I'll tell you the story. It's kind of fun because I was visiting Arjuna at China Lake. He'll tell his version of this, but hopefully it's about the same as mine. And he was having fun playing with these graphical constructions. He was showing me that he could run the heat equation on a graph for the non-local means functional, and it was pretty fast because he had lots of tricks from machine learning to do this. And I took a look at that and I said, wow. I said, Arjuna, we should really do segmentation. We should do the Ginzburg-Landau functional. So that's what we did. So let me just describe to you what it is. So once you have the similarity, once you have that similarity graph, you can start constructing things that look like differential operators, only they're discrete and they're in a graphical setting, and they're typically very non-local, unlike the local operators that we're used to in differential calculus. So we have what's called the graph Laplacian, and that is called the Laplacian for a very obvious reason if you just sort of stare at the formula. So it's the degree of a node if the 2 entries are the same. It's a matrix, right? So it's the degree if the 2 are the same, and if they're different, it's minus the weight. So for example, if you take this definition and you apply it to the standard, the standard 4 regular graph, which is your discrete 2D stencil in 2 dimensions. What we use in numerical analysis for derivatives, right? If you apply it to that particular graph, what you get is none other than the standard 5-point stencil approximation, the numerical approximation of the Laplace operator, appropriately rescaled. Right, that's what you get. So no surprise. But of course, we're not going to apply it typically to that. We're going to apply it to these very different graphs constructed from the data. So that's the idea. So once you have the Laplacian, you can define the Dirichlet energy. This is basically like our H1 semi-norm. There's the Dirichlet energy. And then you can start looking at whether this is the right scaling given a big data problem. So sometimes we have issues with scaling. With certain nodes being more powerful than other nodes. And a common rescaling is this symmetric graph Laplacian where you rescale by the degree. This is a diagonal matrix, a degree matrix. So this is a rescaling that's popular for non-local means in particular. And so we actually use that for a variety of reasons. In our first paper, we used this particular rescaling. And so what we did was we said, hey, let's basically solve the following graph cut problem. What we'd like to do is we'd like to minimize the total variation of the assignment functional. That's the graph cut, which we're going to approximate by what we think is the right Ginzburg-Landau functional. And then we're going to add a term here, which is a least squares fit to known data. And this is what we call this is what everyone in the business calls semi-supervised learning. Meaning that you have a small amount of the data which you know there's ground truth for that small amount of data. That's the semi-supervised aspect of it. And other than that piece, the rest of it is simply a graph total variation minimization problem, which we're not going to solve directly. Rather, we're going to replace that with the Ginzburg-Landau functional on a graph. And we did this kind of, at the beginning, we did this without any theory. We thought, let's just try it. And, because we're applied mathematicians, we're allowed to do that. It worked very well. And so very soon after that, Yves van Gennep, who's actually here in the UK now in Nottingham, he and I looked at developing some theory. So one of the first things we did was derive this gamma convergence result for the discrete Ginzburg-Landau functional for the general graph problem. And we used this form of the Dirichlet energy. And we proved that this functional, notice that there's a constant here that's not epsilon, okay, and there's an epsilon here. So there's a reason why you don't put the epsilon here in the theory, and that's because this is a discrete problem where we're not actually taking differences going to zero. We're not looking at a continuum definition of the derivative here. So the epsilon only shows up here. In some sense, it's a scaling issue as well. So this is our Ginzburg-Landau functional, and we can actually prove it. This is actually an easier proof, believe it or not, than the continuum proof, because it's discrete. So you don't have as much functional analysis to worry about. And you can prove that this gamma converges to this total variation functional, which is nice. So once we did this, we were feeling a little bit better about making this kind of crazy idea here in the original paper. So now let me show you the kinds of things you can do with something like this if you want to minimize this graph cut functional. So here is one. There are lots of toy examples from machine learning, so we of course had to look at them all. This one is called the two moons, and it looks kind of stupid. It looks kind of simple, just a bunch of points in the plane, and that's where you're wrong. If you're looking at this and thinking, oh, those are points in the plane, they're actually not. They're points in 100-dimensional space. So you have to make it a little bit challenging. So what you do is you take sort of moon-like shapes, and then every point, right, you have to have a random number generator which generates a point that is near this shape that lives in the plane, but the point itself and the error associated with that point is in 100 dimensions, right? So it is a high-dimensional problem that you can visualize very simply and that you have ground truth for. And so what we want to do is automatically segment the moons, and these are hard problems because of the fact that the data has a lot of kind of natural curvature to it. For example, the second eigenvector of the graph Laplacian looks like this. It looks nothing like the segmentation. And one thing I will mention, since this is a PDE group and not a machine learning community, the machine learning people have been using lots of ideas related to what I'm going to show you. In fact, that's why that's one of the things that allowed us to get so far so quickly, is because they've already been trying a lot of these things on these problems, but typically methods that are either combinatorial or are purely linear algebra based. So the linear algebra methods, one of the most popular ones is spectral clustering as far as graphical methods go. And so spectral clustering means that you compute the eigenfunctions of the graph Laplacian, and then you do things with them. Basically everything is sort of focused around a few, one or two or three of the top eigenfunctions of the graph Laplacian, eigenvectors of the graph Laplacian. And in the case of the moons is a good example because none of those eigenvectors look like what you want to get. You know, they all look like this. For example, this one, which is sort of cut down the middle. These are results from a few years ago, but at the time we had a recent paper by Hein and Buehler, which was a one Laplacian method, sort of a competing compressed sensing method that we looked at. We had their code, so we were able to compare the Ginzburg-Landau version with theirs. And this was sort of what got us very excited about this general research area, because we discovered that we were, without working too hard, just kind of plug and play, we were able to get more accuracy and considerably faster speed than this code that had just come out the year before. I mentioned Congress with the 435 members of the House. This is what you can do with these kinds of energy functionals with very, very low supervision. So this is an example where we took as ground truth for the least squares fit, we took 5 members of the House, like a few who were Republican and another couple who were Democrat, and we viewed just those 5 as the ground truth, and the other 430 as unknown. So you're relying on the graph cut to do most of the segmentation for you, right? That's really the thing that's going to give you the result. And with 16 votes, we were able to get about 96% correct classification of the party affiliation. And you might say, come on, that's an easy problem today, if you read the newspaper about what happens across the ocean. And so we didn't use today's data, we used 1984 data. Right, so you're laughing, and that's a good reaction, because in 1984, the House was not so polarized as it is today. I like this example. It shows what happens when you work with somebody in the Navy. So there's a joke coming up. You might wonder, why does the Navy care about cows? And the answer is they don't. And that's why we chose this picture, because we had to get it past the people who have to make sure that we're allowed to release stuff to the public. Right? So instead of using airplanes, we better use something that they don't care about. So that's why we chose the cows. The cows have gotten pretty famous because they've been in other papers since then. So, so here are the cows, and this is a non-local means example. So it looks very simple. We identify the cows in this image, and we want to automatically find them in another image. Now, what makes it challenging is that these cows are sitting, and these cows are standing, and there are different locations, and we have no idea what pixels might be relevant for the cows. So we have to do this, in a sense, completely blind. The only supervision is somebody going in and circling the cows in the first image. And the way we did this was using the non-local means graph. And so now if you kind of do the mental math, what you'll discover is that if you look at all the pixels in this image and all the pixels in this image and think about how many weights you'd have to compute for all of those connections, it's an order n squared calculation. You're not going to do that. You're just not going to do that. So this was the trick that we used, taking advantage of, like I said, prior work from the machine learning community, namely the Nystrom extension. And I have a slide later on if I have time about that. But the Nystrom extension is a random sampling method. It's about 10 years old now in the machine learning literature. It's a random sampling method where you compute a random sample of the weights, and you use that information to approximate the spectrum of the graph Laplacian. That's all you're doing, is computing a fraction of the spectrum of the graph Laplacian, and it turns out that's all we needed to do this segmentation. Okay, so now why can we get away with using just a fraction of the spectrum? And this now brings us back to the land of PDEs and ideas coming from numerical PDEs. So if we are, in fact, going to look at a non-convex optimization problem, one of the ways you can solve it numerically is using convex splitting. Namely, you take the non-convex energy and you split it into a convex part and a concave part. Of course, there are many ways to do this. So part of the art is how you do the splitting. And then what you do is you write your gradient descent in the following way. So the time derivative of E, okay, we're going to write as a finite difference with the delta t now on this side. And the catch is that for the gradient flow, you have a gradient of this term and a gradient of this term, and we put the new time level on the convex part and the old time level on the concave part. So this is a well-known trick in numerical PDEs. This is not a new idea. So then the catch is that now to solve this implicit, you now have an implicit equation for the new time level, and what you want to do is to project onto the eigenfunctions of this gradient term. And in our example, for the Ginzburg-Landau operator, that's going to be the graph Laplacian. So we're going to project onto the eigenfunctions of the graph Laplacian. And now what we see is that in order to do this minimization problem of the Ginzburg-Landau functional on graphs, all we need to know to do this is basically all the steps look like this. So we need to be able to do this step here, and this is where the graph problem, in a sense, how to solve it, and the things that we can exploit. Basically, the ideas kind of diverge from what we do in PDEs. So if I were to give Charlie, for example, I'm going to pick you because you're an expert on this stuff. If I were going to give you a phase field problem to solve numerically, and you were going to use a scheme kind of like this, right? Which I know you know this kind of stuff in your sleep. And I was going to suggest that you use a pseudospectral method to solve it numerically. Well, you'd have to pretty much hold on to all your eigenfunctions. Your eigenfunctions of the graph of the regular Laplacian, right? That is the Laplace operator. Those are the sines and cosines, right? If we use the FFT to do that, so this is old stuff. And I mean, one thing you certainly cannot do is throw out 95% of those modes. You have to keep them all. If you want to basically look at a problem, right? So you have a certain resolution you want on your grid, you're going to have to keep all of the modes that you need for that resolution of the grid. So what's really amazing about these machine learning problems is, in many cases, we get to throw out most of these eigen, not like half of them, but like in some cases over 99% of them, which is really, really crazy, but that's true. At least it's true in practice. So what's the big difference between the problem that Charlie's trying to compute using the FFT and the classical sine and cosine modes versus what I want to do here with the machine learning problem. The big difference is that my graph Laplacian I'm constructing from data itself. So it's somehow already linked to the data. Whereas in Charlie's problem, this operator comes from, from heaven or wherever, right? The Laplace operator has nothing to do with the particular physics problem he's trying to solve, other than, you have differential operators in your physics problem. So that's a big difference between these two problems, and so I'm telling you what we do in practice. The theory for why one can do that is still unknown. That's an open problem. And it's, I think, a very interesting problem. So, okay, so I mentioned the MBO scheme, and I promised that it would come back later in the talk, and here it is. So once we got this method working with Arjuna for the Ginzburg-Landau functional on graphs, it was an obvious thing to go ahead and then try the MBO reduction. So this means that we can forget about epsilon. So this is the Ginzburg-Landau functional again. We're going to forget about epsilon, and we're going to replace this with a, am I running out of battery here? Let's see. No, we're good. We're going to replace this with a much simpler idea, namely alternating between the heat equation and thresholding, and there'll be no epsilon. So this is work from a paper that came out last year with 2 of my students. And then this is the idea. So again, the symmetric graph Laplacian shows up here. This is the heat equation on the graph. But notice that we have another term. Why do we have the second term? Because we are doing semi-supervised learning. So there are going to be some nodes for which we have ground truth, and those are going to appear in this forcing term. And then this is the thresholding step. I have 1 and -1 on this slide, but that's equivalent to 1 and 0 on this board. So these are the same. So thresholding. So it turns out that this is, well, obviously this is going to be easy to do. Once you have the heat equation part, that's the hardest part. We're again using convex splitting for this. And then this is trivial. So it turns out this works almost, I think it works better than it does in Euclidean space. Seems to work even better on the graph. And it sometimes can converge in a really small number of iterations. And we have an example with 4 iterations of this. And we get the final state. So now here's how it works. This is the full set of steps for MBO on the graph. What we do is, so we have a graph from the data. We don't necessarily compute it, but it exists. We have a graph, we have a weight function, and we don't necessarily, so we have in theory the symmetric graph Laplacian, but we don't necessarily compute the whole thing. We just know it's there. Okay, now step 2 is the really important step. Step 2 is we need to, now this is where we actually do the calculation. We actually have to calculate the eigenvalues and eigenvectors of the symmetric graph Laplacian, but we don't necessarily compute all of them. We compute enough that we think is enough, whatever we think is enough. This is a bit arbitrary sometimes in practice, but we compute what we think are enough of the eigenfunctions and eigenvectors, typically not all of them. Okay, then we initialize U. We come up with an initial guess for this segmentation, for the assignment function, and then we iterate this 2-step scheme described here. The alternating the heat equation and thresholding. I think my batteries are getting a little bit low, but we'll just keep on going. And so we iterate this 2-step scheme until it reaches a state it doesn't change, and so now notice that I have this in red. That's because this is really critical. We're going to use a lot of very recent ideas from special problems in numerical linear algebra in order to compute these things. So there are a couple different ideas in our work that we use. One is a Rayleigh-Chebyshev procedure, a specific one for symmetric matrices that Chris Anderson published in 2010. He's down the hall from us, so we get the code from him. Yeah?
What defines the way? What defines the norm?
X minus what we
So that's the model. You have to decide on your model. Very good question, because I'm going fast through this, so I thank you for the question. So step 1, you have to come up with a model with a weight function at the beginning, right? But you're not right. But
This is determined.
That's just
determines the whole thing. It determines exactly. So let me say that for these large data problems where you have the order n squared issue, Charlie, and everyone else, there are sort of two things you can do to avoid order n squared. One is that you thin the graph. So right, so maybe you throw out weights that are probably small, right? So that you have to have a way to figure those out. For moderate to small size problems, that's not so hard to do. You can make a sparse graph. And then for the sparse graph problem, we're basically leveraging Chris Anderson's Rayleigh-Chebyshev at the linear algebra stage. But for problems that are really big, like the cow example, we don't do that. What we do is we use the Nystrom extension, which is a random sampling method, and I have a slide on that. So we don't actually compute all the weights, we compute a random selection of the weights to get a way to approximate these eigenfunctions and eigenvalues. So I'll show, if I have time, I don't know if I have time because I've got I don't have a lot of time, right? 5 minutes, right? So, okay, so since I don't have much time, I'm gonna skip, I think, a bunch of pictures that look the same as the other ones, basically same results. The cows are good, yeah, I don't have a lot of time. So I think what I'm going to do is say that what I'd like to get onto are the applications. So I've talked up until now about binary segmentation, but in reality, a lot of problems are not binary. They're actually multi-class. So this is a classical machine learning test problem, the MNIST example, where we have 10 digits, handwritten digits, and we have a collection of pieces of data that are various scrawls, that people have, and we want to try to identify all the digits. And so this is 10 classes, not 2 classes. This is also semi-supervised. This is going to appear, or I guess it's sort of the pre-publication version's already out in TPAMI, Transactions on Pattern Analysis, IEEE Transactions on Pattern Analysis and Machine Intelligence. And the idea is really the same as what I've told you, only a very simple extension to multi-class. So instead of a double well potential, we have a multi-well potential. That's basically the only difference. And the way we represent the multi-well potential is in n-dimensional space for n classes, where the wells are at the corners of the simplex. So you can write down a nice polynomial that has wells at the corner of the simplex. And then you have a small parameter here. This is the Dirichlet energy, and this is the semi-supervised learning part. So that's it. But otherwise, it's pretty much identical to what you do with 2 classes, only it's, and the thresholding can be done the same way. You just threshold to the corners of the simplex. So you can do MBO with this. And the results are really quite spectacular. So here are some examples. This is MNIST. So we have about 70,000 digits, 10 classes we need to get out of that. And we do semi-supervised learning with only 3.6% of the data known. Very small fraction known. So again, we're relying heavily on the graph cut to get the right answer. And so we're getting about almost 97% correct with both of these methods, very fast, 4 iterations for MBO, which is really quite something. And then this is from the literature. This is what's out there for this data set. Some of the best ones in terms of accuracy, like Support Vector Machine, is even a little bit higher than us, but Support Vector Machine is fully supervised. So they use 60,000 digits as known. They know all of these. And then only 10,000 is unknown, right? So it's really not the same problem that they're solving in their case. So we were very happy with that. There are other test problems we've looked at, again, good results. So I like this example because it shows how you can get away with very, very, very few eigenfunctions. This is an example from, this particular example is from hyperspectral video. So it's very, very high dimensional. We have a set of frames of a gas plume release. This is data coming from the US government, but it's not sensitive data. It's data that anyone can work on. And so we have a plume of gas that's released. We're looking at a scene. There's a mountain here, there's sky, there's foreground, and then there's this gas plume. And these are eigenfunctions of the graph Laplacian. These are pictures of the eigenfunctions. We use the Nystrom extension to compute about 100 eigenfunctions associated with 7 video frames together. So we look at and there's no spatial information. What we do, I mean there is, but we don't use it. We use only the spectral information to compute the graph Laplacian here. And so here's our semi-supervised learning problem. What we do is we take these eigenfunctions and we just sort of eyeball them and threshold them in a crude way to come up with a set of pixels in the videos that we believe are very likely to be in one of the 4 classes. And so we've got them, so the plume here is represented as orange, and the sky is blue, and the mountain is green, and the foreground is brown. So this is our known data. This is the initialization, which is random otherwise, and then this is the result after, I think, a small, I don't know, maybe 10 iterations of MBO. So a very relatively small number of iterations of MBO, we get to a steady state, and this is the plume in the different video frames. And what we were very, you might wonder, how do we know this is correct, because there's no ground truth in the data. But the sky, the mountain, and the foreground ought to be the same in all the video frames, because they don't change. And they really are almost identical. And then the plume just moves through the frames. We were really happy with this, in particular because the data is very sensitive to thermal fluctuations, so even the background pixels look quite different from frame to frame because of this thermal dependence, temporal flicker. So we were pretty happy with that. That's coming out in the ICIP conference in Paris later this year. So I think I have to finish because I don't have any more time, really. Right, so I'm not going to do Nystrom, but if you want to hear about it, I have a slide. And I'll just say, this is just an advertisement that we've applied these ideas to problems other than semi-supervised learning. And one particular problem that I'm happy with is work on community detection. This is a manuscript that just came out last year with Hui Hu, Tamal Laurent, and Mason Porter, who's here at Oxford. And it involves looking at a very well-studied problem in the physics literature called modularity optimization. There's thousands and thousands of papers on this in the physics literature. And what we were able to do is show that modularity optimization is actually a total variation minimization problem on graphs. So once you make that connection, suddenly all of this machinery can be thrown at this class of problems, and we have a whole new suite of algorithms which can be very fast for modularity optimization. So that was the point of that paper. And I think I'll stop there, and thank you all for coming.
So, time for questions or comments?
Yes.
So, this is kind of a fidelity term, which I guess is your learning.
Correct.
It's got this with lambda i's, sigma I, lambda I.
Yes.
And you choose the lambda. Your
It's just a
lambda
least
I.
squares fit, right? Yeah, the lambda. Yeah.
So there's a kind of
It's a parameter. So that parameter is very well known in image processing. You have the same thing in all of the image basically what it does is it measures the strength that you want to put on the so in the image case you have to decide how strong do you want the curve smoothing part of the problem versus the fit part, right? And so it turns out to be related to scale, and we have the same thing here. So we'll get somewhat different results if we play with that parameter. You can force the graph cut to have a stronger effect or a weaker effect, and how to choose that parameter is yet another issue. We have found in practice in a lot of our problems that there is quite a wide range of lambdas for which we get almost identical results, so we're very happy with that. Maybe even more so than in imaging, yes.
Is that lambda I greater than 0 for all of it?
Yeah, it should be. I mean, it's right. They're all positive or non-negative energy terms. So you have a positive lambda in front of that one term. So yes, it wouldn't be negative. So the negative issue comes in. So you have these non-convex terms that come in from the double well potential, but even that doesn't change sign. It's just non-convex. Yep.
More questions? So, please.
So I wonder if the algorithm or the model actually can depend on how this weight function Wij Because some data,
Yes.
like you have a network of molecules and they have chemical bonds. And
Yes.
it's not easy to distinguish, say, very similar, just the one, otherwise it's zero.
Yes.
Does the model and algorithm will depend on that?
Of course it does. That's right. So it's a bit of an art how to choose the weight function, and people have been looking at that. So these weight functions are certainly not new, and you can find a lot of work on the discrete machine learning side. You know, looking at things like the similarity matrix and spectral properties. There's a lot of work that's been done on those kinds of ideas. You know, and other kinds of cuts like Cheeger cuts and. So yeah, there's a big literature out there, and I have to say that in the work that we've done, we haven't spent a lot of time trying to analyze that part of the problem. We have largely used the weight functions that other people have already, you know, sort of decided are good ones. In some cases, the problem itself kind of tells you what sort of weight functions you want to use. In the case of the hyperspectral data, you know, for hyperspectral signals, you don't want to use a Euclidean distance in the hyperspectral space, right in the spectral space. You want to use something like a cosine angle because it's looking at the shape of the spectrum rather than the amplitude, right? So there are details like that are sort of obvious, and then there are other ones that are less obvious. But it's a good. There are a lot of very interesting questions here in different directions. Yeah.
One there, one person. Go.
Do you often get stuck in local minima?
Oh, excellent question. We have a manuscript that is coming out. It was a really good leading question because we have a paper with Eagle Bai and Yu-Cheng Tai and my student Ekaterina where we look at global optimal methods, global minimization methods, and we have some examples where MBO gets stuck in a local minimum and the global method does not. And so you end up with a trade-off between the fast speed of the MBO versus the possibility of getting stuck in a local minimum. So for example, with MNIST, what we're doing here is random sampling for the 3.6% of the training data, but you can choose training data that's sort of very badly sampled, and then you will get stuck. So like I'm telling you, the paper hasn't come out yet, but it will. I think it's going to be online like next week or something, and we're ready to submit it. So that's one of the things that we discovered, was that with badly sampled training data, if you sort of force it in one part of the domain, the big domain, you can actually find examples where you get stuck, just as you would expect, John, right? That you would get stuck in local minima. But we do have a way out. So we have a provable global optimal method that takes longer to run, but it works. That avoids that issue exactly.
But the question is, how do you detect with this past method that you are stuck?
That's a nice open problem.
Okay.
Yeah.
Are you running parallel simulations to see that they don't get along?
No, we don't do that. But we do, like I said, we now have a provably optimal method. So you can run, if you're willing to wait for it, sometimes 10 times, 20 times as long, right? If you're willing to wait for it, then it will tell you if it's correct or not. So that's,
Does it also depend on how many eigenfunctions you use?
Well, so now that's another very interesting question. So we've discovered that the spectral truncation, which works so well with MBO, you have to be very careful with the global method. Sometimes you don't want to do that. Sometimes you want to do sometimes you want to do a forward time stepping rather than a implicit time stepping method. So you have to be very careful. Yeah. Excellent question.
So could you do some of the strategies of these problems with traveling salesman problems where they have a tendency
hard,
to
yeah.
get stuck and then they move away just to see if they can get
So, you're asking perfect questions. And in fact, this is an NP hard problem. And the MBO loves to find the easy solution. So I'll just show you a picture. So if you have 2 moons or 3-point clouds, MBO loves this, right? It can find them easily, and it tells you that there are 2, and it tells you that there are 3. But there are these crazy, crazy benchmarks these guys use in social networks called the LFR benchmarks they have power law distributions of communities. They're really nasty examples. And MBO does not, I mean, it does great when you have sort of the easy cases, but then when you get into these complicated mixing parameter cases, then suddenly it runs into problems. So this would be we haven't done it, but this would be a nice problem to try to look at. This is a harder problem than semi-supervised learning because the energy functional is much, there it is, right? So you have this negative term. Charlie was asking about negative terms, and here's an example where the negative term shows up right there in the energy functional. So, right, the gamma does have a minus sign here. And so this is a harder problem, and one has to work harder to get good methods for this. We haven't done that.
Great. I think we thank you.
Sure, thank you.